Hello, everyone. Welcome to the session. Today's session is about Arkane. Um, a lot of these slides were adapted from Matt Johnson and did for 2025. So, um, what exactly is Arkane? If you're not familiar with it, it was mentioned briefly in the previous Arc video. But what it allows you to do is it basically go from your quantum chemistry calculations into actual thermodynamic and kinetic parameters that you can then use in your RMG run or for other applications. It's included by default in RMG Pi. It's designed to be pretty easy to use as a user, and it will automatically do those pesky little stat mech calculations for you in the background. Um, Broadly, and so we'll talk more about the kind of the theory right now. Broadly, from quantum chemistry calculations, we can get electronic energies and zero-point energies. We can get molecular geometries at critical points or constrained critical points, and we can calculate Hessians. Um, and more specifically, what that looks like is, in terms of applications, is we'll use quantum chemistry to find optimized geometries, calculate frequencies, conduct rotor scans, and compute single point energies. And from those, get to relevant properties. And how exactly we do that is through partition functions. So the partition function describes uh, the distribution of energy levels in a thermodynamic system. Um, and it's shown here the classical and the quantum forms of it. And uh, these are convenient because once we can calculate these, we can then use them to get to classical, to like bulk thermodynamic properties. Uh, we'll just quickly review what the partition function looks like. There's four components for uh, the molecular partition function. There's a translational, rotational, vibrational, and electronic. The translational component has to do with the motion of the molecules, keeping all the bond distances the same in three different dimensions. The external rotation is rotation of the molecule, also keeping the bond distances the same. Um, and let me see. We also have the vibrational and electronic. The vibrational component has to do with the vibration of the bonds and perhaps it's related to internal rotations. And you also have the electronic component related to the ability to access multiple energy states. For most species, because the excited states are so high in energy, this usually just uh, falls down to the degeneracy of the ground state. Um, but it is part of the partition function that can be calculated. Um, Once you compute that for molecular partition function, you can also get the system partition function. And from there, it's really easy to use statistical mechanics to get the properties like entropy, enthalpy, and heat capacity that we need for RMG. The great thing is that we don't have to worry about this. Arkane will take care of it for you. And so that's one really nice thing about the software. Um, so far for those we made for the theory so far we made some assumptions that when the molecules rotate externally, the atoms don't move, and that the internal motions obey harmonic oscillator potentials. And this can work okay for some systems, but it's not the best assumption for a lot of other systems. You might have generate lowest energy geometries or similar energy geometries, or you might have rotors that have relatively low barriers. And so this assumption, the RHO won't be sufficient for getting super accurate thermochemistry. So to address that, we sometimes include information from the rotors. So an example shown here. Molecular geometry is often changed by internal rotations around bonds. For example, rotation of the CC bond in ethane shown to the right. Um, these rotations, as I mentioned before, typically have low barriers. And so neglecting that as part of the partition function can have a strong impact on your entropy and therefore your thermochemistry. Um, one common solution that's done is to project this out, the low frequency motion, and replace it with a partition function for a one-dimensional hindered rotor. And so what Arkane can do is after you run a rotor scan to get the potential energy associated with the rotor, Arkane can use this to automatically account for the 1D hindered rotor. Arkane can also account for two or more internal rotors. Sorry, if you have two or more internal rotors, Arkane supports some of the methods for treating those, ND semi-classical and also Q2D Tor for 2D rotors. Um, yeah, so there's quite some statistical mechanical theory here, but again, Arkane will take care of it. Uh, some other things, if you want to get high accuracy thermochemistry, um, quantum calculations are good, but really high accuracy methods are expensive. And so we really want to get the most value that we can from our calculations without having to go to as most expensive a method as possible. So we have a few ways in Arkane where that can allow you to improve your accuracy fairly cheaply. Um, the first is atomization energy corrections, and these correct for basically systematic errors in your QM for each element for specific to each atom. And so these are applied based on atoms. The second is bond additivity corrections, and these include corrections that are fit to certain bond types based on experimental data. And the third is not super commonly used, but it's isodesmic reaction schemes. Those are reactions where the number of each element and type of bond is conserved. And so there's a way to set Arkane up to take advantage of that and the advantageous error cancellation from that. Um, but in general, we recommend using some forms of these AECs and BACs, bond atomization energy corrections and bond additivity corrections wherever possible. And these will be related specific to the level of theory that you use. And the Arkane documentation has a list of like kind of what those corrections are for each level of theory. If you want to get rate coefficients, we can use transition state theory, and again, Arkane will take care of it for us. But here, it's related to the partition function of the transition state and the partition function of the reactants. Um, and the difference in energies between them. And we can get a lot of natural cancellation of errors for these for reactions, and therefore we don't really have bond additivity corrections for transition states. So we recommend it's usually more accurate to not use uh, like such corrections for reactions. Um, we can also include tunneling corrections, and Arkane will like report rate coefficients with and without tunneling when you ask it to compute your rate coefficients. So it can account for that. Um, okay, so this all sounds great. So if you're interested in using it, it's quite easy. All you have to do is call Python uh, wherever you have Arkane installed slash arkane.py and call that on your input.py file. You notice that the input file is a Python script, much like other aspects of RMG. Um, each input file we'll walk through it and we'll see what they look like, but they pretty much all have these four block or one or several most of these blocks. Um, one is specifying the QM level of theory. Two is specifying what corrections you want to include, like atom or bond additivity corrections. Third is defining the species in your system, and then fourth, specify what job to run. And that's basically it. It's really quite um, lightweight and uh, pretty hopefully easy to use. But if you do need some additional assistance with the documentation, especially for running your first few jobs, the Arkane user guide listed here and on the RMG GitHub page, github.io page, has a lot of useful information. So we'll get started and walk through some examples just to give you a better idea of what the input files will look like. So This. So I'm currently in the rmg.py folder. And if you go to examples/Arkane, you'll see there's all sorts of different folders. There's ones for BACs, Explorer, Networks, Reactions, Species. So let's start with thermochemistry. So I'm going to go to the species folder, and we'll start with benzyl. Um, Sorry, actually, I already ran this, so uh, I'm just going to remove everything. Actually, I think I just accidentally deleted everything. So so let's look at a different example instead. This is for ethylene, and I'm just going to look at the input.py folder file. So you can see that it has the four different things I mentioned earlier. It has the model chemistry, which is defining the level of theory that's used. Um, it has the different corrections that we're specifying and just like settings for the run. And then here we're defining what species we want to calculate. So we have C2H4 with ethene.py. Um, and then we specify that we want to calculate the thermo for this species with that label and output it in a NASA polynomial. So you'll notice all we did was specify the species with this label, and um, it'll get the information for the species from this ethene.py file. So if we look in the directory, we also have this ethene.py. So let's take a look at ethene.py. Oops. Um, in ethene.py, we had to specify the bonds, external symmetry, um, spin multiplicity, optical isomers. I don't think you always need to specify that. And then typically you have to specify like geometry, energies, and probably frequencies as well. Um, for this case, we're extracting that from quantum chemistry log files. So you can see here we get energies at different levels of theory. So depending on what level of theory you want to use in your Arkane run. But here we can extract the CBS-QB3 energies from ethene.log. And same for the geometries and the frequencies. Those are from ethene.log and ethene frequency.log. And those are just log files from quantum chemistry. So if we just, why don't we go ahead and run run the input file and see what happens. You can see it's super fast. It's already done. And it will give you an output.py file. And in that output.py, we specified first, it'll kind of list out the extracted information for each of the species. So you can see that here in the conformer, it has frequencies, um, electronic energy, and so on. And then it'll spit out the thermodynamics in a table like this at a different temperature range with heat capacity, enthalpy, entropy, free energy. Um, it'll spit out the NASA polynomial for the species and the temperature ranges over which it's applicable. And so this is um, one of the outputs you get. You also get a Chemkin file that you can use. Excuse me. Uh, you get a Chemkin file that you can use um, based on the thermochemistry. You also get some various other things, supporting information that summarizes it. And you also have plots. So let's check out what this plot looks like. It just, in this case, since we're doing the stat mech, it gives you the heat capacity, entropy, and so on over different temperatures. Um, okay. So let's take a look at now a kinetics example if you want to compute rate coefficients. So I'm going to go to the reactions example folder. I'm going to clear everything just to make it a little more tidy. Um, um, there's some outputs here, but I'm not going to try to remove everything. I'm just going to try to rerun it. So let's look at the input file again. Um, It has the same basic structure as the input file for the thermo. In this case, we've added some metadata like title and description just for our information. We've included here the model chemistry, frequency scale factor. That's basically like an empirical factor um, to help with the accuracy of the calculations. Um, more settings. Then we define the species in the species.py. And we also can define a transition state that has its own um, like uh, Python folder as well, file as well. Um, and now we're defining it in a reaction block where we can label the reactants, um, products, and transition state. I guess this one's a bit weird. So, okay, I see. If you want the transition state for the, I guess it's a bit weird because it has the same reactant and product. Um, but I think if you just want the forward rate, then it doesn't really matter what the product is. I think that's what this example is doing. Um, but in practice, you can also include different product and it'll give you the proper reverse rate as well. Um, okay, so then, yeah, we're specifying we want it to give us the kinetics and the stat mech. So if we just uh, run this again, it's super fast, so it's already done. And just like before, we can check out the output.py folder file and scroll down. It'll now have this block where it gives you the rates uh, at different temperatures uh, without tunneling and with tunneling corrections. Um, and it also give you the equilibrium coefficients, the rate coefficients, and the rate, um, sorry, and the reverse coefficients. Sorry. Um, let's see what else we have. Yeah, and then if you specify it that you want it in a certain like kinetic format, for here it's reporting it in an Arrhenius format, and the parameters are listed here. So it's designed to be pretty easy to use, but we can just take a look at the plot if you want. Um, this has rate coefficient over temperatures. Okay, a couple more examples we'll go through. The first is let's do pressure dependent networks. So uh, if you want to handle pressure dependent effects and explore pressure networks for pressure dependence, you can use Arkane as well. So let's take a look at what the file looks like. It's very similar to before, except that instead of Uh, just as convention for this, not as convention, just for convenience, I guess we included the stat mech and thermo information like um, manually instead of reading it from a log file. But regardless, we're still just setting up the species, and then I'll just skip ahead, setting up transition states manually as well, and then setting up reactions that can happen. Um, Okay. And then, so here's the first new block. It's this network block. In this network block, we have the reactants, which we can label. And we also have isomers. And these are basically, will be treated like unimolecular channels. Um, these are ones that don't have that, like, yeah, that aren't initially reacting, but can be treated as um, unimolecular reaction in the network. And then you can also specify like the bath gas. And after that, you define the network. You can also define, you need to define the pressure dependence, like um, uh, parameters. So here you can specify what temperature range and pressure range to sample over. Um, these are related to the master equation solution that I think we'll talk more about in a later session. Um, and also there's several different methods for doing the pressure dependence that we'll also talk about later. Um, and in here, the interpolation model, this is just like what output format you'd like to report it in. So in this case, want to report it in Chebyshev format. Um, and this is like related to um, the statistical mechanics. So okay, so we can just run this really quick. I'm gonna run this really quick and just see what happens. Okay, so now it's done. Um, you can look at the output.py and just like before, it has all the information saved. So here's um, um, like rates at different temperature and pressures. Um, it also outputs it in a Chebyshev coefficient. And let me see what else. I think that's mostly it for the pressure dependence. You can also like examine the network that you set up. Like this is basically what we defined. Um, and that will be output in the network.pdf file. Okay. Um, so the last thing we'll look at is the explorer function. So from that previous example, we had to manually like set up our pressure dependent network, but in general, you might you might not know exactly what reactions are happening, or you might be modeling a large system and you want to automate some of that discovery. So we also have a function, a feature that lets you explore different channels and uh, explore a pressure dependent network automatically. So we'll just go through a really quick example here. Um, um, because it's doing this automatic exploration, we now need to set up the database so that it has some idea of what species, what their like thermodynamic properties are. Um, then most everything else is the same. Transition state and set up the species. I'm just going to scroll down. Um, we have the pressure dependence block, um, just like before. And now we have this explorer block. Um, and these are just mainly like related to the parameters here is mainly related to like the tolerances for when to like how to explore the network. Um, so I think it's probably easier to just go through an example just to show what it looks like. Um, okay, so let's do that. You can see in the beginning it's loading the database. Um, so it might take a little bit longer as a result. Um, I'm just gonna see if I can find it here. You can see it's trying to, as it's running, it's trying to like grow um, the network. So that's what's happening here. Um, and then you can go to output.py and get like kinetics and thermo for each of the reactions and so on. Um, there's another example actually. I think the second one's a little bit better. So let me run that one actually instead. In this example, I think we're starting with just two or three, or just a few reactants in the system. And then we'll show that at the end of the exploration, it's found like quite a bit of additional like species and reactions that are relevant. In this case, we also see there's two networks that are formed, and this can happen if there's multiple ways the reactants can react. Um, but I'll just show the input file really quickly. We're only specifying like a few species in this. Um, it's really a small input file. But then when we look at the network, um, this is network zero that it found. If you want to prohibit like channels like this where it like finds CH2, you can either limit the number of like the uh, number of like the multiplicity or the number of electrons, um, or you can set a cutoff for the amount of energy species that you'll consider. The second network that it finds is a bit bigger. So now it's found, all sorts of these other different reactions and different pathways that it thinks is important. So this is a way to automatically explore pressure-dependent networks. And in general, yeah, there's ways to get it's pretty simplified input system for the thermo and kinetics and also for pressure dependence and uh, exploration. So hopefully you find that helpful. But that's all I have for the demo today. So I'm happy to take questions.
I have a question. So obviously Arcane and Arc are quite different, but could you maybe elaborate a little bit on the overall workflow? Like would I, for example, use Arc to do quantum calculations and then use the output at the network?
Yeah, so that's a good question. Asking the difference between Arcane and Arc. Um, Fundamentally, they're different things. So Arc is intended to really be like an end-to-end workflow for going from like a smile string, for example, into a full set of the thermodynamic and kinetic information. And that involves automatically running QM calculations and then like plugging the outputs into Arcane and then sort of iteratively doing this process. Arkane is focused mainly on one specific part, which is going from those QM calculations into statistic like thermo or stat mech properties or kinetic properties. So just that narrow part of the um, pipeline.
Makes sense. Thank you.
We have some people raising their hands. How about we go with Renyu?
Yeah, my question is fairly similar to the last one. So for the usual things, is it true that the quantum chemistry calculation is already done and saved somewhere in the RMG distribution, or is usually that we need to make a calculation first before using Arkane?
You'll usually need to do the calculation first. In the examples I showed today, we had already done the calculations and put it in the folder. And so that's why it was so easy to run. But yeah, in general, you'll need to run the calculations, quantum chemistry calculations yourself.
And whereas if using ARC, then that's not necessary, that will be like integrated to the ARC calculation.
If you're using Arc, then it has a chain and can automatically integrate the quantum chemistry calculations with Arcane and that automatically. Okay,
I see.
does that answer
Thanks.
your question? Great. Um, I see if Ferry has a question. I'm sorry if I mispronounced the name.
Yeah, yeah. Okay, that's the pronunciation. So my question was, so let assume that. Hold on, hold on. I just don't know two places. Yeah, back to my question. So, the first one is the installation we had for RMG. Does that also install Arkane automatically, or we have to do the installation of Arkane automatically? That's the first one.
Yeah, so great question. So yeah, Arcane will automatically be installed in RMG Pi. So I'll just show here. It's automatically in this Arcane folder that comes in RMG Pi and also this arcane.py. You don't need to do anything special. It'll be there by default.
Okay. And then the second question is, so do we have to just manually edit the files if we want to run a calculation? We don't need to create a new file, like just the examples are there. We can just edit the files and then like just go on with the calculation, like whatever we want to do, right?
Um, you can either make the files by hand, and the documentation is really helpful for constructing those input files. But yeah, a good starting point might be to start with those examples and modify them. Just make sure that you check the documentation to make sure that you're specifying everything that you do. For example, some of the um, input files, some of the examples might not specify everything that you're supposed to. Like it might not specify exactly like the same symmetry number or like the multiplicity or things like that, and so on.
Okay, thank you.
Just, a cautionary note, if you're using bits of Arkane, but not the full workflow as mostly practiced by the Green Group, you can run into difficulties. There's a group recently used it to just do part of their thing, but they provided the E0 or something, or what they thought was the E0, but what we thought was the E0 was actually the H0, or there's the subtle difference between the enthalpy of formation at 0 Kelvin would be defined relative to the elements at 0 Kelvin, not the elements at 298 Kelvin. And there's some very subtle thing that you'd have to be so specific with the name of the variable that your input file would be ridiculous. So we called it E0 or something in the input file, and then they misinterpreted. And so it took a lot of debugging. It turns out that we think Arkane is not wrong. It's just the documentation is not quite clear enough that it prevents users from making mistakes. So just be careful as the cautionary tale that if you're using bits of Arkane and bits of your own workflow, be really careful that you know what the variables mean.
Okay, thank you.
Yeah.
Hey, this might be more of a chemistry question, but if you're trying to apply corrections to say like a gas phase species with resonance, maybe NO2 or N2O, what type of corrections could you apply? What?
I don't know too much about the resonance module, but I know that we do have some way of accounting for resonance. That follows like kind of like predefined molecular like patterns.
Something's already fit for the cases where there's a resonant.
I think there's some sort of way that it handles the different resonance structures and like each of the individual structures. I'm not aware of any separate corrections on top of that we can add.
But it's not an issue. It can handle this somehow.
It can handle some resonance somehow. It's not perfect. It's definitely not perfect. There's definitely some we'd like to improve on the resonance.
Thanks.
Yep. Let's see. There's a question on Zoom. Is there? My Zoom is glitched, so I cannot see the chat. Do you mind bringing it up? Thanks so much. Fix it, but I don't know how.
The question is Arkane only applicable for non-catalytic reaction or applicable for catalytic reactions as well?
So Richard, maybe.
Yeah. No, Arkane does not do catalysis, heterogeneous catalysis currently.
Are there any plans or to do so?
I'm not sure about adding it into Arkane. Maybe we'll hear about Pinter and stuff from Matt Johnson later. There certainly are tools to do similar jobs, right? In order to get rate constants and thermochemistry from DFT calculations. Yes, we have tools for that. I'm not sure if the plan is merge that with Arkane or keep it separate, but we'll hear more from Matt Johnson later, probably.
Okay.